Hello, everybody. Okay, get started. Okay, so this week is going to be covering global climate change. Really look at my introduction on Brightspace. I try to give hints about each one of the sections of the activities, so hopefully that should really be helpful to you. That I'm going over some things, so I'm going to go over a couple things here just to help you with that as well. Some of it is actually related straight out of the lab as well. Okay, so the first couple parts of this, the first two activities are really going to have you look at the relation between the temperature of the water and the volume and things like that. The second activity itself is actually an experiment that you guys need to do, and it's just with ice and water that you can do at home. If you really don't want to do it, there's video links that you can have in there, and you can watch those instead. If you just want to watch that to see how it's done, without you having to recreate it. But one thing to really look at here is if any of you have taken Gen Chem, then this should be really useful because if you took Gen Chem, you probably remember this. This is the ideal gas law, but it really has a relation to things like density and stuff like that. So it's not just related to gases. And this will help you if you think about this equation and how it changes, will really help you with that. So in chemistry, whenever we have equations like this, these are in equilibrium. So whatever is on this side is the same that's on this side. Okay. We don't really have to worry about these two in this equation when we're talking about this because N and R are going to be constant. So this amount is going to be the same. This is a gas constant. So we don't really care about things like that. Okay. Since these have to be in equilibrium like this, if you have an increase on one side, then you have to have a corresponding decrease on the other side. Okay. So if you have a say like you increase the volume on this side, the only way to offset that is if you increase the volume here, you have to decrease temperatures over here. Okay. And the same. So any increase of one of these on this side will cause a decrease on this side, and increase on this side will cause a decrease on one of these on this side to keep it in equilibrium. So that's something that you really need to think about when you're looking at the first two activities here, because it's going to have you ask the first part asks about salt water and fresh water. And just by even looking at this, so salt water that's down here is blue, the regular water is red. So fresh water floats on top of salt water. And that's simply because you have more stuff that's dissolved down here. And when you have more particles that are dissolved down here, that makes this more dense. So this will sink down to the bottom and fresh water will float on top of that. Okay. So you're going to be looking at that again, just based off of what it's asking you in the first activity. But in the second activity, you're going to, again, do some experiments with ice and water. So hopefully that'll work out. Maybe it'll be a little bit fun for you to do something instead of just reading the manual all the time. Okay. The next parts of it are going to be related to carbon dioxide in the atmosphere. So this is called the Keeling curve, and this was started back in 1958 in Mauna Loa Observatory in Hawaii, where they've been measuring the changes in CO2 every year since then. And you can see that roughly back here in 1958 when it started, we were roughly at maybe about, I don't know what this is, about 315 maybe. Okay. And all the way up here to 2015 to when this book was written, now we're already up to 400. And if you go and look at this, which I do think that the lab requires you to go look at what it is, I believe the current ppm is somewhere around 420. So we can see that even in the last 9 years, this has increased more. Okay. You will notice that it has this sort of sawtooth look, and that's what this is over here, expanded out where it goes through. This is all seasonal changes that happen. Okay, so you have an increase right here. These are in your winter months when it's going up because you have all of the plant life, primarily in North America, because that's where all the land is has not bloomed yet or is dead and has decomposed. So you have an increase in CO2. When spring starts to happen into summer and you have more plants growing and absorbing CO2, then you have a decrease in the CO2 in the spring, summer months. Once you get to the end of the summer and start going back into the fall and the winter, then plants are dying off, they decompose, they release all the CO2 that they've taken in, and then you have an increase again in CO2 back until you get into the spring of the next year. Okay, so these are just cyclical based on season. And then the black line that goes through it is the average as it goes through all the seasons. But you can see, regardless of this, we are still increasing in CO2 all the way up here. Okay, so there are going to be some questions in there that are related to this, and there are going to be related some questions that are related to this as well as to, hey, why does this, why do you have this up and down cycle? I actually think that what I gave you is one of the answers to one of the questions there. Okay. Ice cores, you're going to be looking at this. This is the figure from the book that you're going to be using. Ice cores can record changes in atmospheric composition and temperatures over hundreds of thousands of years. So you're going to see with this is 800,000 years of climate record based off of ice cores. When you're looking at these, this shows the accumulation. These light layers that are in here are what accumulate during the summer, where you're going to have less ice accumulating. And then the darker layers, the thicker bands that are in here that you can see here and here are your winter months, where you have more ice accumulation that's happening. Okay, so you can see a seasonal variation in here. This over here shows interglacial periods, and it shows all different things that change throughout these times. Do you have more insolation? Insolation means solar radiation that's coming in. Are your temperatures higher? Is the sea level higher? Do you have higher levels of CO2, higher levels of methane, higher levels of deuterium, which is a form of hydrogen? What is the oxygen ratio with this? When you have more glacial periods, so what you have is so oxygen has two isotopes. So you have 16O and you have 18O. Okay. So this lighter oxygen right here is what is primarily in the seas, and it gets evaporated first because it's the lighter of the two. So when you have more evaporation and then you have precipitation that falls onto land, you have more oxygen 18 left over in the sea. So when this gets on land and gets frozen into glaciers, it actually gets locked up in the glaciers. So when you have interglacial periods, you have more 18O in the ocean. So what you're going to have is there is a ratio, which is the 18 oxygen over 16 oxygen. So when you have glaciers present, this will be higher because this number is lower. That makes this ratio higher. Then, when you have periods where it's warmer and you have interglacials like this, then when you have no glaciers, this goes down because this number goes up. And when this number goes up, that makes this ratio smaller. So we'll be able to see over here that there's a correlation to that. When you have less glaciers, you should have higher temperatures. You should have a lower 18-0, 16-0 ratio down here when you don't have glaciers because this will be liberated from the glacier and melt and run off back into the ocean. Okay, so this is just trying to show you all the different how all these relate when you have glacier and interglacial periods. All the pink vertical stripes here are interglacial periods, so that's when glaciers do not exist. Okay, so that'll be helpful when it's asking you questions about the activity itself. All these pink lines here are when there were no glaciers, okay? And all these other times are when you did have glaciers, okay? Sea level rise, this is the last part, and it only focuses on San Francisco. This is just in relation to where if you have glaciers melting, so at that, what is that going to do to certain coastal areas? They listed a bunch of things in the manual. I didn't want you to do all of them. I wanted you to look at San Francisco. And this is a different map that I picked out, but it's similar and will help you in answering this. So these areas right here in the dark blue are just areas that are going to get quote unquote deeper. Okay. So you're going to have more water here along the coast. These inland areas here with the blue, and this, like I said, this isn't from your manual, but it should be similar. These innards here with the lighter blue are areas that are going to experience flooding as the water level rises and moves in. So you can see as this water comes in here into San Francisco Bay, all of these areas that are around here, this is where the water extent is going to reach. And this is going to flood a lot of cities because there's a lot of population in cities that are around this area. Okay, even San Francisco that's sitting here will end up experiencing a problem. This will experience a large problem down here because if you remember from our lab where you did looked at the subsidence in the San Joaquin Valley, and since this is dropping and since the water is going to come in, all of this water can just flow into this area. Okay, so it's going to ask you some questions on the last activity, just in relation to what is going to happen in this area should sea levels rise. And it's kind of obvious and intuitive that a lot of these areas are going to flood and going to be overtaken by water. Okay, so that's it for this week. If you have any questions, please let me know. Email me. I'm here to answer anything, or come to the Zoom hours. And other than that, it shouldn't be too terrible of one to get done. But if you have any questions, please, please, please let me know. Okay. Thanks, everyone, and have a great week.